Valentino Braitenberg he's not dead. He was a neuroanatomist. I know him personally. I actually had it on foot interactions with him. Very interesting figure. He was a quantitative neuroanatomist. That is someone who really counts the synapses in the brain. He made an atlas of the mouse brain with this long-term collaborator Schütz. I think she's still active. I'm not sure. Maybe she's retired now. So they wrote a famous book about the mouse brain that says, how many % of the synapses of this kind and that kind. And it's very interesting. It's a whole field. And so one of his main emphasis always was that the brain is so strongly recurrent. He's the author of some of the evidence for that. And he taught at a neuroscience summer school I think in Corsica or Sardinia or something, for many years, principles of neuroanatomy, and invented this way of doing that, which I'll illustrate now through one of his vehicles, and which I think is very interesting. And he has written a book. It's called Vehicles, and it's still in press. And if you can find it, it's really fun. It has like 35 or so vehicles. I'll explain in a moment why it's such an interesting metaphor, the vehicle. It actually turns out that it's a whole research program, and one could say some of our activity is making Braitenberg vehicles work, because actually most of them don't work if you really build them, because they're lacking dynamical principles, I would say. So he used these to illustrate principles of neuroanatomy, like for instance, if you have ipsilateral structure versus contralateral, and you sort of functional difference that makes. We'll look at an example like that. The irony is that this has become a metaphor for a certain style of robotics. Some robotics is called behavior-based robotics, where people try to stay away from very abstract representations, world models, computations on, and try to do everything like reflex-like building a robot essentially from reflex loops. Actually, an old idea, but that was advanced very much because Braitenberg illustrated how you could get even fairly cognitive-looking stuff using just very simple circuits. Again, they don't actually really work in practice so well, but you can make them work if you add essentially dynamic properties and so on. That's our research program. That's why I'm using this as an introductory story. We'll later not really be working like that, but the intentional agent that I will ultimately show could be viewed as a sophisticated Braitenberg vehicle, even though, frankly, you will not recognize it. It's just so much, much more complex than Braitenberg maybe envisaged. So I'll take you through one of these Braitenberg vehicles to make some points. Ultimately, the goal of this lecture will be to get you a sense for behavioral dynamics. That's not a point Braitenberg makes, actually, but that actually one is naturally led to when one looks like that. So you use the word vehicle, and that is really just an organism that moves through its environment with its own motor system and has sensors as it moves through the environment. So that's so this is I drew that, but in his book it's also at that level. He himself is not really a great graphical artist. So this is the vehicle, this square, this rectangle. These are the wheels at the back, like Formula One car wheels, right? That will be so broad that you don't have to worry about stability. And it would have to have some support. This body would just drag along the surface and solve these problems. Real robots usually have the wheels in the center. And then this will be a sensor, and that's a cable that connects the sensor to the motor. So that will be, discuss that more in a moment. And the notion that it's a vehicle is essentially that it's an agent that when it acts, it moves, and it moving will be informed about the consequences of its action because its sensors move with the vehicle, and therefore it will be in closed loop. And that's what's typical of vehicles. And in my robotics class, I actually emphasize that that's different from robot arms. Almost all animals are vehicles in that sense because they do most of the action in a way where the sensors that guide the action are moving with the actuator. Now, if you put a camera in your hand, then your camera is in a vehicle because then you guide the hand through something that moves, right? And for instance, when dogs do something, they take their snout and then try to dig into the ground. They don't typically use their paw. They do this in a limited sense, but a lot of the activity is with their head on their snout, and then they behave vehicle-like. And there's actually some argument in the robotics community why that's a good idea and why it's easier to work that way rather than have the sensor somewhere else and then just act with something on the sensor. Because it's more abstract. They have to make a computation what that hand would have to do given my image here from that camera. You can imagine it's more abstract. And some humans and some primates, very few animals actually do that well. Almost all the animals are vehicles. That's how I came up with this idea of vehicle. The question? No. Okay, so I'll take this apart. So he emphasizes that you need 4 things. I always add the 5th thing. I think you need 5 things to understand behavior. So one is to know what actuators are there or effectors that can make movement. What kind of sensors do you have to be informed about the environment? Your nervous system, you could think of the nervous system as connecting the sensors to the actuators in terms of some inner currency. In the nervous system would be maybe spikes or activation. And then a body which connects the sensors to the actuators in a mechanical sense. Right? And the vehicle would be where it, for instance, really provides, they move along with the body. And you can imagine there could be more complex arrangements, like if you have all these, there's a lot of these hair cells which are essentially measuring something elastic. If you deform something, then you're informed. Like the hearing is based on that. So there are more subtle forms of mechanical coupling that could come about. The 5th thing that's not always emphasized so clearly is that you also need an environment that is structured in a way that's appropriate for that vehicle. In evolution, it's the other way around. The vehicle is adapted to that environment, so the vehicle is adequately structured to deal with the environment. If you build a robot, you actually have to think about the environment that robot will work in. And you will see that the Braitenberg vehicles are very much sensitive to that. They work well only if the environment has the right scale, the right kind of sensor information. So with these 5 things, rather than just 4 things, function may emerge. And I'll take you through this example of one of those vehicles. So before we do that, let's dig a little bit deeper. So what do we mean by sensor? So sensor is ultimately an interface from something outside the nervous system to something inside the nervous system. So this means it's something physical. We call that here an intensity, some physical variable is mapped onto something internal to the nervous system. Here I call it activation. In the brain, in many nervous systems, it would be maybe spiking of neurons. There are some non-spiking neurons, actually, especially in early sensors, that just translated into a membrane potential of something inside, right? So this mapping is often characterized as a function. I mean, input output. Given intensity, you have a unique activation level. When it is monotonic, here's a straight line, just because I can draw straight lines more easily, but it could be just anything monotonic. Then people talk about that being rate code. In the sense, there will be a one-to-one mapping. Given the activation, you could say how much intensity you had out there. That is not always necessarily 100% true, but there's a first approximation, right? So that's abstractly speaking what a sensor is. And of course, real sensors are way more complex than this. What is a motor or an effector system, an actuator? That's the reverse, right? There is something that takes a neural thing, an activation variable or firing rate, and produces something physical. Here makes movement. Like if this is this motor, maybe activation is like a voltage, and you drive this motor, and then there's a certain turning rate of that motor. In the muscle, it would be maybe a force that is generated, something physical. The activation coming down the brain sends out something to the muscle. Actually, when you think about that, that turns out to be a little more subtle than that. So if you just think about even just a robot, all of you, anyone who has had a toy car ever. And I have now a grandchild, so I can have the opportunity to buy stuff like that. Then you know that these toy cars, electric toy cars, right, will drive much faster on this ground than on a carpet, right? So you see there is already something about coupling to the environment. So it's actually a dynamical system that's coupled to the environment. And if you know anything about the human movement system, you know that muscles have reflexes. Without reflexes, they don't work. Reflexes means also it's a closed loop thing, and that is actually a dynamic system. So actually, it's not just a function, it's actually a dynamic system that has one input, one contribution to its equation, that is that activation. It turns out the sensors are also like that. Now, sensors are also dynamic systems, and you all know that. I don't know if you all know, but many of you might know that, for instance, sensors have maybe a certain frequency range in which they work. That reflects actually that fact, because they can only follow a signal when the signal is slow enough. And when it's too slow, they make a lot of errors. So there's a certain range of time changes that they can follow, and that's because they are actually dynamic systems that are ultimately entrained by the internal input and then to the system. That is often negligible because they're kind of too subtle for a lot of the problems we're looking at. So more easily discarded. But in the motor domain, this is very important. But I'll ignore that for now. I'll just say that in anticipation of what will come later. Okay, the body is kind of simple, right? That mechanical linkage, for instance, in the ideal case, they are just rigidly linked. In reality, it's not like that. Even bones are elastic, and we're actually elastic robots. That's a very hot field of robotics right now, because the rigid robots have a lot of drawbacks when they interact with surfaces. And that's one of the reasons why robot soccer sucks so much. And the actual robots really differ very much at the level of the actuators and their bodies. And we're not so far along doing something more human-like. So even the very cool Boston Dynamics robots, still any human outperforms them. You have to look more carefully what outperform means, but I can argue about that. Okay, and so the nervous system, of course, links these two things. And this is like certainly the most trivial nervous system, and we'll not look at anything more complex here in this lecture. But could have loops, right? And that will be then recurrent. So this is a feed-forward neural network. And when you put it into an environment, it actually is in some sense recurrent, because now it will sense, there will be consequences from its early action. That we'll get to that. Okay, so the environment will be structured. So here, in this simple case, we're just thinking about something physical that has an intensity, and therefore its structure would be how is that intensity distributed in space. So I drew this also with a drawing program, and if this is some intensity variable, there could be regions of high intensity and regions of low intensity. In some of the examples, people think about a source of some intensity. It could be light, or could be sound, or could be temperature, or something like that. Temperature is like an easy to visualize thing. We have different temperature zones. Some animals regulate their body temperature just by going into the shade or into the sun. They're essentially using the spatial distribution. And you might, in light of what we'll be talking about in a moment, you can imagine it makes a difference if what the gradient is. If these zones are of the right order of magnitude, like of the body size, then the agent could perhaps be sensitive to the change in temperature. While if the temperature has, it was extremely high spatial frequency, would say that is, that it varies very strongly, like 1 millimeter, and the temperature already varies. Then for an organism that is a meter broad, that will be just noise, and therefore that environment would be unstructured. Right? But for a little bacterium that is maybe 1 millimeter in size, that might be a meaningful environment. Right? So you can already see that needs to be some register between the kind of environment you're looking at and the kind of organism and its nervous system that we're looking at. So here, this is there are 4 basic vehicles that Braitenberg discusses, and these are the four that really work well. And we have a robotics lab class where you build one of those, and I picked the taxis one. The other ones are a little not as useful, let's say. And the higher vehicles all need some fixing for them to really work. And so the taxis one is maybe the most. I can tell you the 4 are where the 2 sensors are connected ipsilaterally, and then the alternative is contralateral. This sensor goes here, and that sensor goes there. And then you get a permutation by saying, is the sensor characteristic negative monotonic or positive monotonic? and the motor, is the motor the same or different? You can swap that. Which one has the positive or negative doesn't matter. Then if you count, there are 4 possibilities. That gives you the 4 things. So this is the one where the sensor characteristic has a negative monotonic shape, and the motor characteristic is a positive one. In other words, if you put a lot of activation in the motor, they turn rapidly. That's what this means, right? And the sensors, if you put a lot of intensity into the sensor, it responds little, which actually photoreceptors do. So it has a negative monotonic characteristic, right? And so the claim is that that vehicle will have taxis behavior. That is, it will tend to orient toward sources of that intensity. And ultimately, if it gets close enough, it might even stop moving. And ultimately, to make it more homely, you have to have some idea of how the intensity falls off, either with distance, or you can also think that there could be something about the angular sensitivity, depending on what kind of sensor you have. And then it's maybe intuitive. If you have a situation like that, then the sensor that's closer to the source will get higher input than the sensor that's further from the source, either because of the distance or because of some angular arrangement. And so when you do that, when you have that in mind, then the mental simulation goes to say, this sensor is closer, so it gets more intensity, so its activation is lower, and therefore it's just a lower signal to this motor, and lower signal to this motor means this motor turns less, and so this wheel turns less always than the other wheel, and if this wheel turns less than that wheel, then the vehicle will turn to the left until it's heading to the source. Both sensors get the same input, right? Motors get the same, and then it will be perfectly going straight. So this is like a verbal way of deriving something like that, which what I'm deriving here is that when the vehicle is heading, let's say, to the right of the source, it will turn to the left, has a negative turning rate. If it's on the other side by symmetry, it would turn to the right, toward that source. So its turning rate, so the change of its heading, must be a monotonic function, negative monotonic function of heading direction of its current orientation. And there where the heading is 0, that's when it's heading to the source, and it will be going there. And this is actually a dynamic system, because this here is the derivative of that. Dynamic system is really that you have a variable x, and x dot is the derivative, and the derivative is a function of x. Next week we'll formalize that, right? And this is a dynamic system. It's a dynamic system that has a 0 crossing that's called a fixed point. That is, this is a solution that's constant. Once you're heading there, you will keep on that heading direction. And the negative slope makes it an attractor, that is, it attracts neighboring solutions. So if you start a little bit to the right, you have a negative turning rate, you will get to head more toward this and start to the left and so on. So you will be attracted, right? I have a little formal derivation of that, which not even sure I need to force you to go through. I can do that, yeah. Now, if you don't follow that, you can reproduce it later at home. I should say in the exercise, I'm asking you actually to reproduce this mental simulation. And in doing so, you will discover that we made a lot of implicit assumptions about symmetry, about how steep this is. You can imagine if it's steeper, then it makes more difference, and a couple of things, and that makes you aware how useful it is to have an actual model rather than just sort of this hand-waving kind of theory that is very, very common in neuroscience, right? Almost all of neuroscience is using these hand-waving stories, and this little exercise to show that it is useful to be more precise, because qualitatively different things can happen depending on those details. Okay, so this little math derivation takes a couple of steps, and it's also sort of an illustration at a somewhat different level that concrete models help. So to make this mental simulation more concrete, I have to have a model of all of the components, right? I already hinted how to have models of the sensors, of the motors. The body essentially it's just a model how the motors will change the entire configuration. That's also easy to derive. When one wheel turns faster than the other, we can do that. The one thing that we don't have a model is the environment. And so I'm hinting that we do, this would be a model of the environment where we say the intensity depends in some way on the heading. It doesn't matter now if it's because of distance effects or because of the angular characteristics of the sensor. And so in a sense, this model combines properties potentially of the sensor and the environment. And so that would mean that if you were to rotate the vehicle on spot, the intensity sensor would get would have a maximum when it's really turned to the source, and then it would have less of a maximum. It doesn't have to go to zero, right? It's just some function. And so if you look at this vehicle with the two sensors, then you could say, let's look at the two sensor characteristics like that for the left and the right sensor. And now, again, it depends on whether you're looking for distance or for angular orientation. Some subtleties about that, whether the sensors are mounted like this or like that. But in that case, you could say, well, one is sensing something a little bit further to the right of that curve, and the other a little bit further to the left. So when I take the difference between the intensity on the left and on the right, I can say that will be essentially the derivative of that. Right? So, for instance, in this regime, the left minus the right is a positive number, because this minus that will be positive, right? And somewhere here will be a negative number, because this minus that will be negative, and in between has to go through zero, right? So you will get something like that, roughly speaking, when you take the differences in intensity left versus right, and this is a function of the direction in the world where the sensor is pointing, the heading direction. So these are these top two graphs. So from this model of the world or the sensor, I can come to that model. And now I have to translate this into differences in turning rate. And the differences in turning rate, so if I have differences in intensity and differences in turning rate, that's just the motor characteristic. So the motor characteristic just says activation and turning are monotonic to each other. So when I apply that to take a difference, it doesn't change anything about that. So I can just replace a difference in intensity by a difference in turning rate. So there will be that monotonic relationship between these two. And so now what I do, the last step is I take the heading direction and look now, here I have the difference in intensity left-right, and that I pass through this here to get the differences in turning rate, and this is a negative slope, so it will just flip this function around and make it a function like that. Now, if you apply a minus to a function, it just flips the function. And then I have this curve, and this is the curve that has that, this is this dynamical system turning rate of the vehicle as a function of current heading. That's a dynamical system, and that has this attractor. And that's the derivation of the dynamics, right? So I know that it's something you have to do on a piece of paper and really figure out yourself. I didn't ask that in the exercise because it's a bit more theoretical, but it would be useful for you to try to figure that out. So that's the derivation that, I have more steps here in between. But this is a description of what that mathematical formalization of what that mental simulation does. So we call this a behavioral dynamics. So first it's a dynamical system, as I've said several times, and we call it behavior in the sense it is a dynamical system where the variable that is the dynamical variable here describes something physical, describes the body here, heading direction, body in space, right? And so it's actually, you could say it's a mechanical, but it's not mechanics in the physics sense, right? It's what the nervous system, this whole organ arrangement, the nervous system, the environment, there's a model of the environment, of the sensors, of the body, of the motor, the nervous system in there that together lead to that. That's what that leads to behavior, right? And this will be a behavioral dynamics that describes the behavior as emerging from a dynamic system where you just need to know the initial state of the vehicle, of course, in its environment, right? The sensor model, the world model included some assumption about where the source is. So when you start, that's the equation you have some starting values, and then this will predict the future of that of behavior in this case, right? So the mental simulation is some kind of simulation of that dynamic system. There's actually an online simulator for that, but I wanted to reserve that for another lecture I'm giving somewhere else. So some of you might experience that later. Good. So that's the notion of behavior dynamics. Now, for those of you who don't know dynamic systems, this might be a bit mysterious. So next week, I'll actually really explain what dynamic systems is and attractors and so on. We'll formalize that. That will be the example that you can have in mind. So I'll now build on that just to make a few additional points, but that's sort of luxury from now on. So the main point is for you to understand this behavioral dynamics picture. Good. So one point to make to contrast that perhaps with biological cybernetics. I wonder if I should actually do that, or maybe I'll skip that because many of you don't even know that. Yeah, maybe I'll skip that. I'll be happy to discuss it with anyone who's interested in that. So instead, let's look at a next step. So far it really just does one thing. It goes to the source, right? Now, if I put two sources into the environment, then you could be intuited that it can do already interesting things. It could, in one case, if the sources are far enough so that there is a trough in intensity between the two, then that will mean, if you think of that derivative, right, that is sensitive, the two senses essentially sensitive to the spatial gradient. It's in the angular gradient of the intensity. So they will notice that it goes downhill here. And therefore, if you think about that, the dynamics that will result will have one zero crossing that's an attractor at this peak and another zero crossing at that peak. So two attractors. And in between, there will be zero crossing with a positive slope. That will be a repeller. So it will essentially matter if initially it was heading a little bit to the right of that minimum, then it will be attracted to this maximum. Or if it was initially oriented a little bit to the left of that, then it will be heading to that maximum. Yes, please.
I have one question in general. Maybe that's exactly what you just explained, but also in the graphic before. On the x-axis, many arrows pointing probably towards the effector.
Yes.
Okay. But I was kind of confused.
So, I mean, these arrows just, it's a vector field, so that every point you could have a vector that is the rate of change. Now, so another way of plotting a dynamic system is not to plot the rate of change as an axis, but to just take any point, any of these pens left. So I could go into the just this axis of the heading direction phi, let's say, and then at every point I make a little vector that is pointing. This would be phi dot. So the rate of change of phi might be d phi by dt. And so the direction would tell me which direction it moves, and the length would tell me how strongly it moves. A dynamical system like that. Then here the vector is positive, that will be increasing, so point to the right, and with a large length. And then let's say here it would be already a shorter length, and then the length really goes to zero. And here it's negative, it points to the left. And the length would get larger and larger as I go over, right? And so for every point on this axis, I have a vector of the same dimension, so pointing along this axis either to the left and right, and length of the vector is the rate of change. This is sometimes called a vector field. And that's what I'm trying to indicate with these arrows. So I'm only making a sample of only 4 vectors. Yeah. This is the axis vector. Yes, that's right. Sorry. Yeah. Oh, I see. Yeah. This is just the indicating the axis here. Should make a different kind of vector for arrow for that. Yes. Yeah. So here you see that this does a little bit more than control cybernetics. I didn't want to take you through all the details of doing the cybernetic calculation. Cybernetics really just always means that you are thinking of a set point and then the error, the deviation from the set point. You're minimizing that, and that's a concept that only works if you have a unique thing that something is an error about, right? The deviation from one unique state. Like if you have a heating system or a climate machine, it's supposed to have a set point, a certain temperature, and then it should reduce the distance of real temperature from that temperature. Very trivial kind of thing. That's what a control system is. Cybernetics essentially glorifies control. And so that's fine, but that is really extremely limiting. If you have a system that can make a decision to go left or right, for instance, then it's already a different story. You see, then you can't really say what the error is. There's one error relative to one goal, another error relative to another goal. So they have to think a little bit differently and have to think about the underlying dynamic variables. If you move these yes, please.
Like if the body is a bit to the left or to the right, in which direction it would go, but if in a perfect world we would be able to position the body in like directly in between those sources.
Yes.
How would this then behave? Would it just stand in one spot or would it go?
That's a good question. So in mathematical terms, it means that your initial condition is exactly that repeller. So you have zero rate of change, right? And you could be stuck there. And in practice, it's the fact that the dynamics is not purely deterministic. There's always some noise. Some non-deterministic component could be a sensor noise, could be physical environment that the intensity fluctuates, could be some sensor noise, or could be even neural noise that your nervous system doesn't transmit these values precisely and has some fluctuations that leads for the state to deviate randomly to the left or to the right, and that will make a decision. And that is true, and this is a real issue. So we have some stories, I'll later be able to refer to those, where that plays a role, where you're essentially in decision-making. This is a form of decision-making, right? A selection decision. In decision-making, you are sensitive to noise. And that's how you can bring out any kind of non-deterministic aspect in behavior. So, and that's quite special. So there's always noise, but it plays that critical role only around certain states. Now, typically, it will not be that you are. I'll actually explain a little bit more about that in a moment. Yeah, is that enough at this point? Yeah. So we actually claim that that's real. That you're really using noise to disambiguate situations like that. And all our models contain noise, and it really matters for kind of models we'll be talking about. Now, the next point is actually critical for that. And so I come back to that question 2 slides down. And so if I just move the two sources closer so that the distribution fuses, right? It just depends on the nature of these sources. Then you can see, if I make that kind of derivation, I will get again a single attractor in the middle. There will be some kind of averaging, right? You're moving to the center of gravity of the source. Here, I assume the two sources are symmetrical. Generally they might be one is stronger than the other. Then it will be, somewhat biased, not the mean, some kind of biased average of these two. And you see, that's qualitatively different behavior, right? Here you select one of those two. Here you average them. Between those, it's actually a bifurcation. You could think of the distance between the sources as a parameter. You look at a family of different situations, vary systematically the parameter, and there will be a range where they're fused, and a range where it's this bistable, actually selection decision. In the middle is this repeller, and there's a qualitative change. At some critical distance between the sources, you can start to select one of those sources, right? So this capacity to make a decision emerges from some change in the environment. And that is actually how this noise story comes out, because in actually, so you would say, yeah, so there is this one initial condition, and if I have that, then I make a random decision. Well, it's almost never the case, because usually one source is larger than the other, and so it's very odd for you to be in that initial condition. But because we'll find that a lot in our modeling, that we actually systematically go through bifurcations like that. We're happily in an attractor, and suddenly it becomes unstable. And typically what happens is that a repeller or some other kind of object, dynamical object, remains at this location. And it's at that moment that noise becomes very critical. So it would be not somewhere here making a random decision by just sitting there. No, it would be doing that. This happens, for instance, the distance between the sources might become larger because you get closer. Now it's angular. It's actually angular decision. As you get closer, the angle becomes larger, and at some point it splits. Previously, they were fused. And that's when you make the decision. And that's when the noise can really make macroscopic effects. And we find all across the models that we'll be looking at that noise is critical for ultimately non-deterministic responding, for probability. You know, when you do any psychophysics, you have a probability of responding. Very rarely do you have 100%. I mean, you have saturation. But in other cases, you will have a certain probability of responding. And that source of uncertainty comes from noise that becomes effective at a bifurcation like that in instability. And instability means pushing you very close to an unstable state, but you are pushed there because you were in a stable state, and that stable state lost its stability, and now it suddenly becomes unstable. So this is this, sometimes there has been this terrible debates about free will, and it's totally, I mean, terrible in the sense of this is a good example of interdisciplinary problems, right? Because the people from different fields, like some physicists, say, "Oh, there is no free will because now some quantum mechanics is just nonsense." Because of the concept of free will comes from a discipline, ultimately comes actually from law, from moral philosophy of what is right and what responsibility means, and so on. So a very different kind of context. And to say that is just determinism in a mechanical sense, this is really misunderstanding. So if you're interested in non-division, so that's what I'm saying, it's not a question of free will. Free will is a moral concept. It's but a question of determinism. So how do you explain that you don't always get the same behavior when you make the same environmental condition? And that's, you can see the seed of that comes from noise plus bifurcations. Yeah. So let's forget about that. So last step here I want to make in this introductory lecture is that this is, if you say decision making is the simplest form of cognition, one could say that, right? I mean, what is cognition? Cognition is when it's no longer just all determined by the stimulus. Now, stimulus response, that's really sensory motor, automatic. And when you now have, that's no longer uniquely determined, your behavior is no longer uniquely determined by the stimulus, then you have some minimal form of cognition, you could say perhaps. But this is here, of course, still a very trivial kind of decision, because here it's your mechanical state in the world that determines what you're going to do, right? To call it decision making is a little bit an interpretation, because if you're initially oriented more one way, you're going to do one thing, and the other way you do the other thing. And that's because we have a purely behavioral dynamics that it's the physical state of your body that determines your future. And so the next step will be to say, what about a case where I make a decision, but I don't physically act it out? I'm looking at these two things and I say, oh, I'm going to turn to the left one, but I don't have a go signal yet. So, for instance, the total intensity is not enough to get this going. So how could I then represent that inner state that now I went there? Now you see, I need something, an inner variable that tells me the difference between having selected this one and that one. And that ultimately will be our notion of neurodynamics. I will say there are some inner variables, some activation variable that stands for one choice, and that has also a dynamical system, which is in an attractor for being activated, and the other one for the other choice is deactivated. And that will be then the inner representation of the decision to go left, which we can then act out separately under some conditions. And of course, it's somewhat arbitrary to think of a neuron that represents this target. And the more natural thing will be to say there is a neural map that maybe is spatial or in orientation, so that along some dimension, what could be here the angular spatial representation, for instance, that there are activation peaks, and there could be an activation peak that is centered on this source. There's input for the other source, but that peak wasn't realized because there's some inhibition that suppresses it. That will be concretely how we do it in the field. And so this inner state of activation will represent the decision. And it could even happen in the absence of the sources. So you could even have a case where you remove the sources, but you store your decision that we call working memory. When you're able to keep those peaks activated, even if the input is removed, then you would have a way of storing that decision that will be working memory. So you see that's where we will be going. So we'll be talking about neural dynamics rather than behavioral dynamics. In fact, in this lecture, I'm not going to return to behavioral dynamics. Go for the summer semester for that. We're really only talking about this kind of stuff as a dynamic system. And you will see that it's similar as, this looks almost the same, except this is a neural variable, activation variable, rather than a physical variable, right? But it's again the same thing, rate of change over the variable, dynamic system, fixed point, negative slope. And then when we do this for the fields, it's just an infinite dimensional dynamics, so many axes, so we can plot it in the simple way, but we'll get a way to think about it along the same lines. And actually, it turns out that requires a neural network that's a bit more complicated than this feed-forward one that has some loops, inhibitory loops, for instance. Good. Yeah. So these 5 things that are listed there, sensors, effectors, bodies, environment, that is the prerequisite to getting, it's both sufficient and necessary to get behavior out of the behavioral dynamics. And so what we'll be looking at is to get the higher Braitenberg vehicles, in other words, they need neural dynamics. They need other ways of internally representing the states of the vehicle. And that's what in Braitenberg is a bit fuzzy, because it's all just mental simulation. It just writes down a diagram and a story. And then if you actually, like, here's a story of how to, this could count. And we actually will see sequence generation, we will look at a counter. But that requires some inner dynamics. It's not just one neuron triggering the next and so on. That doesn't really work. So we're making that work, and you'll learn about how to do that in this lecture.